So this is the fifth lecture that I'm going to upload. Recall that in the last lecture, last time I defined what are irreducible actions and how any action can be decomposed uniquely into irreducible sub-actions. It's like sub-action by sub-action. I mean, if you have this is the set on which the group is acting, then I can decompose X into disjoint union of G invariant subsets and then you can restrict the action on these subsets. So these actions are called sub-actions. So I will write this is a decomposition of this. Right. And this is unique because in fact the unique decomposition is just precisely this, where U is the collection of representatives of distinct orbits. Okay, so firstly, let us give some examples of such irreducible group actions. So remember, group action is irreducible if and only it has exactly one orbit. That is, the group action is the action is transitive. Yeah. So now talking about examples, let's see the first one. Consider this group, the permutation group on n elements that is acting on this set by just taking any sigma from that group and any element I, it will map to sigma of I. That is where the element I is sent by that permutation sigma. Clearly, this is transitive because if you pick any two elements, call that set X from X, then obviously you have this permutation, right? So this is in sigma, and that will take this is in Sn, sorry, and that sigma will take your I to J. Yeah. So this is transitive. Now consider the subgroup uh, sorry, this subgroup of all even permutations, that is A, and consider the same action, A acting on the set of n elements 1 up to n by again sigma and I goes to sigma of I. Yeah. Now what about this action? See, firstly, uh, so here n is at least 3, yeah, because for n is 2 that is obvious because there are only two elements, 1 and 2, and you can then that is very obvious. Like A2 is what is A2? Like it's just the trivial group, right? Because S2 is just isomorphic to Z2 and A2 is a proper subgroup of Z2. So yeah, this is trivial group. So this action will not be transitive because there is only one element, the identity instance. Yeah. Anyway, so we are doing it for in at least three, and in that case, say you have two elements ij from that set X, again, I'm denoting it by X. Then you can take this three cycle, and of course you can take this if none of I and j are equal to one. Then call it sigma. This is a even permutation. So this is in an, and this will take your I to j. Yeah. And in case you have say if one of them is equal to one, what will you do? Like you need to take like you take one element, you take I and you take one. Then again take this permutation, right? This this is in A and this will take your I to one. So in either case, this is transitive. So both one and two are transitive actions. Yeah, these are two very basic examples. So, and another example of a group action is which we'll need in the next videos or also in these videos. Consider group G and a subgroup H and act G on the set of all left courses. This is a collection of all left courses. So, H in G. So this action is again pretty much the left multiplication. Right. But is this a irreducible action? That is the question. Like if this action has only one orbit, say suppose then if it has only one orbit, then what will you? This will be orbit of some GH, right? And um, then any element of take two elements, for example, take say this element E that is 1 dot H, which is actually H. This is also a left cosine, right? And this can be written as G inverse of GH. And so take any other, say XH, and or I should do it in this way. Let's do it in this way. Say take any XH and YH from this. Then just XH if you act YX inverse is the element of the group. This will map XH to Y. So this is a transitive action. Right? Pretty much trivial. Right. Because inverse exists in a group. That's why any left such like any such left multiplication is a transitive. Because you can connect any two points of the set by means of an element of G with like taking inverses and all. So this is this. And now so we get some examples of transitive action or irreducible actions. Yeah. Now see, suppose you have two actions like in group theory. What we are mostly interested to classify things, like, to classify up to isomorphism, right? So here again we will talk about isomorphism between group actions. So for that, in a group, what you do? You take a homomorphism and you add the bijectivity condition. That is the one onto and a homomorphism. So here again the one and onto condition has to be there, and the homomorphism part of course here because see the set X has no structure, no group structure. So you cannot be talking about group homomorphism. That is too much to ask for. So here you can take what are called the, let me define them first. This is just G invariant say maps or G invariant function. Which is this? Say you have two actions. I'm denoting actions by this action of G on X and action of G on Y. You have two group actions, and G invariant function is the function if between X and Y such that this is same as G dot f of x. Now these two dots are a little bit different, right? That is clear from the context because the dot in this side, left side, is the dot of the action in x, and dot in the right side is the dot that is the in the action of y. So that is pretty much clear from the context. So I'm not writing it with like dot one or dot two. So again, like so you can denote it by this diagram. See. This is your function f, so it will take any x to f of x, and this is just multiplication by g. Multiplication means the group element g is there. So it will take this fx to g dot f, right? And here again this the action of g. So this will take x to g dot x, and this is the function f. So it will take f of g dot x, and these two are same. So that means this diagram is commutative. So that is what we mean when we say uh, a function is G invariant. Yeah. And moreover, and if there exists a 1 onto G invariant map between x and y, then Gx, these two actions are said to be isomorphic. Are said to be uh, isomorphic. That's why I'm denoting it by tilde, the usual isomorphism notation. Said to be isomorphic. Yeah. Now the question is, so now I'm stating a state like stating a claim like I'm claiming that suppose you have an irreducible action, right? This action of G on X is irreducible, suppose. And remember this example 3. So I am stating that any such irreducible action of a group on a set X is same or same means isomorphic here, of course, isomorphic to uh, action of G on uh, set of left cosets of for some subgroup H of G. Like there exists some subgroup. So suppose G acting on X is irreducible, then it is isomorphic to an action of G on G mod H sorry, for some H in G. That is just a subgroup. It is not a normal subgroup. Yeah. So now this is the claim. So what do you need to show? You just need to find uh, such a G invariant bijection between X and G modulo H. So basically, you need to find two things. Firstly, you need to find such suitable subgroup, and secondly, you need to find such a G invariant 1 and onto map. Yeah. So, what is the candidate for such a subgroup? That is the main question. So, see, and what is this action here? This is just the again the left multiplication action. So, just G and XH goes to GX H. Yeah, this is the action. So now what will you do? Firstly, fix one element of X. Say fix some X in X. And so see, naturally you have one subgroup. Whenever you are talking about an action, you naturally have this subgroup. See all those elements in the group G that fixes X or stabilizes X. This is called the stabilizer of the element X in G. Yeah. So I will denote it by G subscript small x. So this is subgroup that can be easily checked. This has the identity element. It also satisfies this binary operation and all. I'm not going to do that here. And see, so this is subgroup. Gx is a subgroup of G. So naturally we have this one subgroup in hand. So what will you do? Firstly, so and what is this? Then if you take this and this action will just be G some I need to take H X is there, so maybe I can take G1 acting on G2 bar. Okay, G2 bar means the coset G2 GX. You know what I mean. So this is just G1 G2 bar. So, and remember this action is irreducible. So you need to use that fact too. So what does it mean? Irreducible means this uh, X is just orbit of this, right? You can take any such X. So I fixed one X and I have taken that X is orbit of this small x. Yeah. So what means it is just G dot X. Right. So now you have the candidate for H. And secondly, you need to find this F. Right. Remember, you need to find this map, and also this should be G invariant bijection. So let's see. And actually, it's pretty clear because see, any such element of X is some G dot X, right? G dot small. So if you take any such, say, Y from capital X, then that will be some G dot X. So we have a candidate for a coset representative. Just take this. Yeah. So now observe that. So the first thing we need to check is whether this is well defined. That is the thing we need to check because here Y can be like Y can be G dot X and also some G prime dot X. So you have two, G and G prime. So we have to show that this is actually independent of that choice. So let's see that. So suppose uh, that say Y is G1 dot X as well as G2 dot X. So then what this implies? G1 inverse G2 stabilizes X because that is acting on X is X. So G1 inverse G2 bar is just the class of identity in this GX subgroup in GX, right? And that implies that G1 bar is same as G2 bar. So this is well defined. And if you just reverse these arrows, you will get this is 1. So you get F is well defined plus 1. Yeah. And onto is again very obvious because you can take any such H bar from this and then just consider H dot X. So this shows F is onto. Now the major thing you need to show F is G invariant. And for that, that is again actually not very difficult. That is actually you can see because what do you need to show them? To show G invariant, uh, you need to show that this G dot X is same as G dot Fx, where the dots are in the dots corresponding to corresponding actions respectively. So I'm not saying that that is clear. So see here G dot X is, or I think let's do it in this way. Hmm, let's see how we can do it. No, I'm mixing up the notation, so I can't take it. Fix. So let's see. Let's do it in this way. Take any, say G G1 from G and say Y from X. Yeah. Right. So what will I get is just see. Now Y is some G dot X and this G is independent of the choice. Like this is independent of the choice. G, this map that we have already shown. So you can take any such G. So then by associativity of the action, you will get this dot X and that is just G1 G bar, right? And on the other hand, you need to show that what is f of y, right? So you can write it G1 by G1 or sorry. So let's see what is G1 f of y. This is G1 dot. So G1 dot f of y is f of G dot x. That is G bar. That is again G1 G. Right? Because again you are acting G1. So in either case you get the same thing. So f is G invariant and F is a bijection, so we get Gx is isomorphic to G, comma G modulo G of small x. Yeah. So any such irreducible group action is essentially the same as group G acting on left cosets of a certain subgroup of G through left multiplication. That is what we get. Now let's see some useful corollaries to it. Again, see, so here we assume that the action is irreducible, but you can always take, say, you have any action, okay, where G is a finite. So this is the situation, and so you can fix any element, and then you can restrict this action to orbit of x, and this is always irreducible, right? Because there is only one orbit. Yeah. And because this action is irreducible, and remember we have a bijection from G, sorry, from X, that is here the main set is orbit of X. So we have a bijection from this orbit of X to G mod G of X. Right? So both of them have the same cardinality because group is finite and the set is also finite. So you can talk about their cardinality. And so from here what we get order of G is order of the orbit of X, and this is just order of the stabilizer. So that is called the orbit stabilizer. Orbit stabilizer. That is or the cardinality of orbit of X is same as the index of the group stabilizer of X inside the group G. Yeah. So this is your orbit stabilizer. This is an easy corollary in case both of them are finite. So that's one of them. And now, secondly, so let's say another example. So, example of a group action. And now that we have orbit stabilizer theorem, we can like talk about a lot of counting arguments that I promised in the first video, the introductory video, that those computations will be really easy to handle. So let's see one or two of them. Then I'll finish this video. So let's call them applications. So firstly, the first theorem that one usually study in groups and subgroups, the Lagrange's theorem. So let's see how we can do it. So suppose G is a finite group and H is a subgroup of G. Act, say, act, what action should I take? Let's see. Say, I can act G on the set of, say, mm, let's see how I can. Uh, I can act G on H, right? I can do it by left multiple. Yeah. So then what we get? Then from the then this set your age is a set. So this will be the disjoint union of the orbits. And see what will be the orbits. So the orbits will be, see there are R orbits, okay. Because group is finite, so there will be finite union orbits. See there are R orbits. And or I'm sorry, it should be action of H on G because That is obvious because you need to multiply one element of H and one element of G and need to land inside G again. So that need not be the case if you act and like if you take the set as H, it may land outside of it. So, yeah. This is your action. Then then your set is G. Then this can be written as uh, say orbit of some there are many orbits orbit of x1 to x2. Now what is orbit of x1? Orbit of x1 is just this x1 times this, right? Because what is this action? Any such H and G goes to this. So orbit of xi will just be, or let's do in this way. Maybe. Whatever way you can take this. Follow this. So this will be just hxi, right? So anyway, I can just switch it. But this hxi, uh, this has a bijection to the set this because any such hxi you map it to h. This is a one element that is. So you have h and r. So what you get is cardinality of h divides cardinality of h. This is your Lagrange theorem. Yeah. Now the second example. Sorry, I just messed up in this situation. So this should be the subgroup acting in the next application. You may take, say, you have H and K, two subgroups of G. With say G is a finite group. Let's talk. Then you can consider the direct product, right? The external direct product of H and K. That is just the ordered pair of H comma K with the usual component wise multiplication, like binary operation and all. You know that, and that you can act on say G. Take G as a set again, like the last situation. So any such this and G will go to this. So firstly, to wave it is an action that is not very obvious, like the last ones. You actually need to check whether the two properties of the actions are going to be satisfied or not. But again, if you take G to be 1, then sorry, if you take sorry here, you need to take HK to be 1, right? Because that is the group here. So that will take this element G to G and H1 K1 H2 K2 of G, that is uh, first act according to the group law, that is H1 H2 K1 K2, then acting on G, this is H1 H2 G will be K2 inverse and then K1 inverse. And again that is same as H1, first you act H2 K2 on G K1 inverse, but that is again same. No, I'm not writing. This is just a group action, it's verified. And so you have the orbit stabilizer formula, right? Then take this orbit of this element identity. What will be this? This will just be uh, say HT inverse, right? And you need to take this inverse in order to get the associativity correct. You can't just take HG and K only. Yeah. So then, but that is the set HK, right? Remember, this set is just elements of this form. And what is the stabilizer? These all such pairs such that HK acting on 1 gives again 1. That is HK inverse is 1. That is H is equal to K. That is also this. H belongs to H and also H is equal to K, so this should belong to this. So this is just the diagonal elements of say H intersection K if you take it the Cartesian product of H intersection K with itself. So not let's take the cardinality and this will just be same as cardinality of this. And so orbit stabilizer theorem. This is the orbit. This is just stabilizer and the acting group is H cross K, but that has cardinality. Yes, so you get this formula. Yeah. So let's see, just see, this is just one line argument of this action, and you take the orbit stabilizer theorem into account, and that will just follow easy. Yeah. So you get these two applications, and so I'm not going to talk anything in this video. This is already a bit too long, it's more than 30 minutes. So yeah, so just recalling. So in the last class, I talked about irreducible actions and decompositions. In this video, I just gave some examples of irreducible actions. Then I talked about what are G invariant maps, and this is the main theorem. You can call it a theorem. Uh, see, this is just a theorem. Any such irreducible action is essentially same with this action of G on for some suitable subgroup, the multiplication of left quotient. Oh, sorry, left multiplication of any element with elements of left quotient with that subgroup. And from that, we reduce the orbit stabilizer formula. And with the help of orbit stabilizer formula, I showed you this particular uh, group action. And if you take the stabilizer of this element identity, we'll get this counting order. And the first application is just the application of, say, just the application of group action and the fact that it partitions the set that I talked last class. That is just an equivalence suggestion. That is. So that will give you the Lagrange's theorem. And let's see, let me define just one more thing. Then I will finish it. I will just start from there in the next video. So, so you have this. Okay. You have this notion of all such elements which fixes x. So you can take these two, say all such elements of x. So both are essentially what you are doing. You are just taking this ordered pair such that g dot x is this. So in one hand you are counting the all such first component that is this, and you are just taking the counting the second component, keeping g fixed. Yeah. So this is called the set of fixed points of this action. Yeah. And in this case, the orbit of x is just the singleton x, right? Because you are if you act any g with x, you will again get x. So in this view, you will get cardinality of x is just the orbit of x, which x belongs to u. But you can do even more with this. It's like you can take all those elements which has just the which are the fixed points. You can just take them outside. All of them have the orbit. All of them have singleton orbits. You can just take those singletons together and take it a set as x power g. And you can take the other, say, uh, or maybe, yeah, I'm sorry. So, and the other ones will be all such x, such that x is in EU, but it is not a fixed. Yeah, and you take the cut. So this is the class equation, or I should class equation in general. In the next video, I will talk about the class equation in particular for a group, and then I will also prove result counts regarding the number of orbits that you get in an action with help of these two sets, the fixed point set and the stabilizer. Yeah. So that's it for this video, and I will see you in the next one.